Hello, everyone. Welcome to the Math 111 video lecture on section 3.1, which is Introduction to Polynomials. So let's start with a definition of a polynomial. A polynomial is a function built by adding or subtracting non-negative, which means 0 or more, integer powers, so no decimals, no fractions, non-negative integer powers of the variable, which I'm just going to call x. So, for example, quadratic functions are built by adding or subtracting non-negative integer powers of x. You see that we have two x squareds minus 3x's and a 9. Now 9 doesn't look like it's a power of x, but remember that x to the 0 is 1. 0 is a non-negative integer. So 9 is 9x to the 0. So that constant term belongs in polynomials, no problem. Here's some other examples. Negative 1/2 x cubed minus 3. Even though that coefficient is a fraction, the important thing is that the power isn't. X, or let's say y equals mx plus b, that's a polynomial. So a linear equation is a type of a polynomial. And even constants, y equals 7. 7 is a polynomial because it's a non-negative power of x. It's 7x to the 0. Some functions that aren't polynomials well, they include exponentials. These are not polynomials because the x is in the power. It is not a power of x. Logarithms are not polynomials. The square root function is not a polynomial. I can write that as x to a power, but notice that power is a fraction. It's not a whole number, so it's not a polynomial. And functions where there's a term in the bottom, not a polynomial. Now I could write that as x to the minus 2, but this is not non-negative, right? It's not 0 or more. So again, it's not a polynomial. So you'll know you have a polynomial if all your terms are positive whole number powers of x, potentially with a constant term. Sorry, I forgot to record when I did that. So quadratic functions, we're going to start with those. And quadratic functions are polynomials, as I just showed. And let's do a brief review of factoring. So there are 3 levels of quadratic functions that we're going to factor. There's simple ones where your x squared is just by itself. Then there might be ones where the x squared is not by itself, but that leading coefficient will factor out very easily. This should be a 10, I think. Wait, no, it's 12. And then there are ones where you could factor out the leading coefficient, but it's not going to make the rest of the quadratic function look easier. So there are basically three levels. Another example here is maybe if you have a fraction as your leading coefficient. And we're going to have different techniques for each of these. So let's start by factoring x squared minus 7x plus 12. And I use the box method. If you have another method that works, that's fine. If you don't, I recommend using the box method. I think it's straightforward and it handles most common cases where you actually want to factor. So what I do is I say I have x squared minus 7x plus 12, and if it factors, it should be factored into x minus x1 times x minus x2, where these are numbers. I don't know what those numbers are. But I know if I were to multiply it out, I'd have x times x, which gives me x squared. And then this constant term 12, that comes by multiplying the x1 times the x2. So I can put 12 there. And then the negative 7, it has to come from these two pieces here, because there's going to be a x term here and an x term here. And so what I have to do is I have to find two numbers that multiply to 12 and add to negative 7. Now, there's a lot of possibilities, not just integers. I could use fractions, but if we're going to go to the fraction world, it'll be too much work. So in general, if you're given a quadratic function where the leading term is 1, there's a good chance that these numbers here are going to be integers. And so let's try it. Let's think of all combinations of numbers that multiply to 12. Well, 1 and 12, 2 and 6, 3 and 4, and they should add to negative 7. Unfortunately, when I add these pairs of numbers, I don't get negative 7. I do get a positive 7. And that should remind you that I'm allowed to have integers. So I could also have negative 1 and negative 12, which is negative 13 when I add them, negative 2 and negative 6, which is negative 8, and negative 3 and negative 4. And negative 3 plus negative 4 equals negative 7. I have found the two numbers that multiply to be positive 12 and add to be negative 7. That means one of these boxes has to be minus 3x. The other box has to be minus 4x, which means along the top I have x minus 3, and down the side I have x minus 4. That little line right there represents a minus sign. And so my factored form must look like x minus 3 and x minus 4. All right, so what do you do if the leading coefficient is not a 1? So let's look at this next example I had, which is 2x squared. We're going to factor 2x squared minus 10x. I'll go ahead and make this a plus 10x just for fun. Plus 10x plus 12. I changed my mind. I want this to be a plus 14x. So I'll rewrite it. 2x squared plus 14x plus 12. Well, you could do the box method carrying around that 2, but I think it makes more sense to factor the 2 out of the whole polynomial before you do your factoring. 2x squared plus 14x plus 12 equals 2 times x squared plus 2 times 7x plus 2 times 6. And then you can do the box method on what is now a quadratic with a coefficient of 1. So I'm going to draw my box. And I have an x plus, and an x plus. So I get an x squared here and a 6 there. So I need two numbers that multiply to 6 and add to positive 7. Here are all my integer combinations. And if I check all of them, you might not need to check all of them. Because you see right there that 1 and 6 add to 7 and multiply to be 6. So that must mean you have a 1x in that box and a 6x in the other. And your factors are x plus 1 and x plus 6. But don't forget, you still need the 2, because that's still a very important part of your quadratic function. So bring the 2 all the way down, and then build your factors x plus 1 times x plus 6. All right. Next example, let's factor 3x squared minus 13x plus 7. We might look at this and say, okay, let me factor that 3 out first, but then I get 13 thirds and 7 thirds. And as soon as I go into fractions, there's no point in trying to find a fraction that multiplies to 7 thirds and adds to minus 13 thirds. There are just too many possibilities to check. So I recommend that you switch from this symbolic form to graph form or picture form and just graph it with Desmos. So let me pull Desmos up here. And I put my function in. Don't forget the 3 at the beginning. 3x squared minus 13x plus 7. And those two places, the 0.63008 and then 3.70326, those are the two places where my function touches the x-axis. And so when x equals 0.63008 or 3.70326, when x equals one of those two values, the function equals 0. And that means if I put x minus 0.63008 as one of my factors and x minus 3.70326 as another of my factors, and then remember you still have that original 3 out front, this is my factored form, because if I put x equals 0.63008, this first term would be 0, and I'd have 3 times 0 times another number, which equals 0. And if I chose x equals 3.7, etc., then I would have 3 times a number times 0, which equals 0s. So the factors of a quadratic function tell you the x-intercepts and vice versa. You know the x-intercepts, you can build the factors. That's how I recommend that you factor complicated quadratic formulas, or sorry, quadratic equations or quadratic expressions. For the simple ones, you should try doing it by hand. But when they get complicated, use the tools that you have. In particular, use the graphing ability along with your knowledge that the x-intercepts tell you the factors and vice versa. Let me give you an example of that. I'll draw a graph with a couple of x-intercepts on this quadratic function. That point right there is negative 2.5. And this point right here is positive 2. That means when x equals negative 2.5 or x equals 2, the function equals 0. And that means my factor x plus 2.5 times x plus 2, sorry, x minus 2, will build a quadratic function that has these x-intercepts. Because negative 2.5 plus 2.5 is 0, and positive 2 minus 2 is 0. Now there's some unknown leading coefficient, which represents a vertical stretch, right? This is a function, so is this one that has the same x-intercepts, and so is this one. All right, so the A I can't tell from my x-intercepts, but the factors I can tell from the x-intercepts. Okay, so let's take this idea from quadratic functions and extend it to polynomials in general. Any polynomial can be written as a product, so as a multiplication of factors. Now, if we allow ourselves to have factors with complex numbers, they're actually very simple factors. But even if they aren't, they can be a product of factors. So for example, I could write a polynomial. Let's see, let me come up with one. The polynomial x cubed plus 2x squared minus 5x plus 6. I could write this if I knew the x-intercepts, which I do because I built it. I could write this as x minus 1 times x plus 2 times x plus 3. Because my polynomial will cross the x-axis at these 3 points. The x-intercepts of a polynomial correspond to factors of the polynomial. Let's ask another question about this polynomial. Let's ask about the y-intercept. Well, the y-intercept is when x equals 0. And with the polynomial, it's super easy to figure out what that number is, because f of 0, I'm going to use the same polynomial, 0 cubed plus 2 times 0 squared plus 5 minus 5 times 0 plus 6. But every time the x is 0, that term drops out, and we're just left with the constant term. So the y-intercept of a polynomial is the constant term. All right, so far we focused on the x-intercepts and the y-intercept of polynomials. And those are important pieces of information. There's two other types of information that we care about with polynomials. The first is we care about turning points. And the second is we care about end behavior. So a turning point on a polynomial is a local max or min. If you recall back to chapter 1, a local max means it's the highest point in a small neighborhood, and a local min means it's the smallest value in a little neighborhood. All polynomials have a shape that includes 0, 1, or more turning points. So a polynomial might look like this. And the turning points are the local minima and the local maxima. This one has 4 turning points. And you can tell something about how many turning points a polynomial has based on the formula. If the largest power, called the degree, in a polynomial is odd, then the graph will have an even number of turning points. That's guaranteed, up to 1 less than the degree. So for example, if I have f of x equals x to the 5th minus x to the 4th plus 2x cubed minus 7x squared plus 3x minus 4, then we usually write it with the largest power first. The degree is 5, which means at most 4 turning points, possibly 2 or even 0, because 0 is an even number. So my possible graphs, just sketching them very roughly, could look something like 1, 2, 3, 4, maybe like this. 1, 2, 3, and 4. Or it could look like 1, 2, and it could potentially have no turning points, which might look something like that. Now it's flattening out, but that's not going to be a maximum or a minimum, so it's not a turning point. That's if the largest power, if the degree is an odd number. The other possibility is that the degree is an even number. If the degree is even, but not 0, this breaks down if the even number, the even power is 0. So if the degree is even, 2, 4, 6, etc., then the polynomial will have an odd number of turning points up to 1 less than the degree. So if my function was, let's say, negative x to the 6th minus 2x cubed plus 5, I'm not bothering with a lot of the interior terms, but the degree is still 6 because that's the largest power. Then I could have something that has 5 turning points, 1, 2, 3, 4, and 5. 1, 2, 3, 4, and 5. Or it could have, let's see, 3 turning points. 1, 2, 3. Or I suppose it could have 1 turning point, which would look kind of like a parabola, but it tends to be a little bit flatter near that turning point. So those are my options. They're odd numbers, and the largest possible odd number of turning points is 5, which is 1 less than the degree. Okay. That covers turning points. Now let's talk about end behavior. And that is what happens to the outputs when the inputs approach positive or negative infinity. End behavior, so the ends of the graph. Ends of the graph. And this is also related to the degree. So remember that the degree is the largest power. It also depends on the leading coefficient. The number multiplied by the largest power of x. So let's take my first example from the previous page. I'm going to change it just a little bit. 7x to the 5th minus x to the 4th plus 2x cubed minus 7x squared plus 3x minus 4. The degree is 5, and that's an odd number. And the leading coefficient, abbreviated LC, is 7, which is positive. And what that means is, in terms of the ends of the graph, it's going to come up from negative infinity, do a bunch of stuff here in the middle, don't know exactly what, and then it's going to go up toward positive infinity. And one unfortunate thing is that usually this here is not written the arrow coming up. It's usually given a down arrow like this. That's how you're going to see it. So that's how I'm going to write it. So it goes down towards negative infinity as x goes towards negative infinity. The way you decide your end behavior is using a quick decision table. End behavior of a polynomial. By the way, this only applies to polynomials. And the degree has to be at least 1. Again, this breaks down if it's a 0-degree polynomial, but we usually call those constant functions. So the easiest way to think about it, I think, is to make yourself a little square. I like to use boxes in math. And then think about your degree. And there are 2 options for a degree. It could be even or it could be odd. And then think about your leading coefficient. And there are 2 options we care about for the leading coefficient. It could be positive or it could be negative. And each of these pairs gives you a different end behavior. If you have an even positive, that's going to look like a parabola when it gets very big. So it goes up in both ends. Unless, of course, the leading coefficient is negative, which makes it go down on both ends. An odd degree polynomial comes up from the left and keeps going up to the right when the leading coefficient is positive, or it comes down from the left and keeps going down to the right if the leading coefficient is negative. Have this in your notes. Use it whenever you're asked to figure out the end behavior of a polynomial until it becomes second nature. All right, so that covers all the ideas for polynomials actually completely. Y-intercept, x-intercepts, turning points, and end behaviors. Y-intercept, that's just a constant term. X-intercepts, these are determined by the factors. It's the opposite of what you see in your factors. The turning points, this is told by the degree. Is it odd or even, and how big that number is? And the end behavior, which requires both knowing is the degree odd or even, and also is the leading coefficient positive or negative. Now, I showed you there are two different ways to write polynomials. There's the standard form, which looks like 7x to the fifth minus 3x squared plus 2x minus 9, where you just list your powers of x as you go down. And then there's the factored form. This is a different polynomial. Now let's do negative 1/3 times x minus 1 times x plus 2 squared times x plus 3. And the x plus 2 squared, there's nothing wrong with writing that. It just means we have 2 of my x plus 2 terms. So if I needed to find out the y-intercept, I would prefer standard form, because then I could just say my y-intercept is -9. If I have to figure out my x-intercepts, I would prefer the factored form, because now I can say my x-intercepts are 1, -2, and -3, and the -2 actually appears twice. If I need to figure out the turning points, I need the degree. Well, that's really easy when it's written in standard form. Here the degree is 5. But it's actually also really easy in factored form, because each of your factors contributes an x, so they contribute to the degree. The degree is 4 because there are 4 x terms in the factored form. So I know that this function g of x has at most 3 turning points, which is 1 less than 4. It could also have 1 turning point. And I also know the end behavior. Since it's a negative leading coefficient and an even degree, that means it goes down on both sides. When it's not written out, when it's collapsed, you can still count the degree, because you have 1x minus 1 plus 2x plus 2s plus 1x plus 3. That's still a degree of 4. That wraps it up for this video. The next video will look a little more closely at drawing the graphs of polynomial functions.